Hello, everybody. I think we should be good here. So I'm running just a little bit late here. If you followed me on Twitter, I mentioned that I now have a drawing tablet for it. And unfortunately, it was a little bit of a lie when it says that it's going to be entirely plug and play. So I am just finishing the setup there. Because I think the first thing we're going to start tonight doing is just recapping what we've done so far. So in the past 7 episodes or so, we've gone through so in the past 7 episodes, we've built a fuzzer, we've got some crashes, we triaged them, and finally exploited them. So, let's see how well this works. Supposedly, I need to restart my computer before these will work. That may be a lie, because I already saw it grabbing my input. So let's see. So if all of this works the way that it should work, I should be able to come over here. And no, it did not work. Well, it kind of worked. Ooh. Sorry, I am playing with my toys. Okay. So this is going to take a little bit of getting used to, but what? Can I not just delete that easily? So, where were we? Right. So we're going to go through the exploit and everything that we've been doing so far, because it's actually a little bit complicated, everything that we've done so far. And I think it's a good idea to have one clear single place where we can talk about it reasonably. So let's see if I can actually do that. So the first thing we did was we built this fuzzer. Actually, I don't need to draw that. We're going to actually pull it up for you. So the first thing we did here, where are we? We're going to go here in the middle, projects, Python. So this had 2 pieces to it. Our basic fuzzer, we had our little C-types module, which is this thing right here. And it's relatively simple. So we have 3 functions we expose through C-types into Python. We have this first function here, which is the handler. Basically, well, actually, let's start here. With the init. The init just sets up a massive buffer. The reason it's this big is in order to take advantage of some properties of malloc. We know that this buffer is going to be away from all the other pages. And the reason that's important is in case we have a heap overflow, we don't want to actually accidentally trash the stuff we're doing, because we're doing in-memory fuzzing. So when the C-types module starts up, we initialize it, we make some space, we use signal to register a SIG-SEG-V, or a segmentation fault handler. And what this does right here is if the current process gets a segmentation fault, if it's a SIG-SEG-V, the OS is going to pass control to this handler function, which is up here. And that's, again, relatively simple. We're going to say we're going to print out a statement about it. We're then going to create a file name. It's a unique file name. We're using a stack pointer as a unique ID for this, just because it's already randomized. We don't need to randomize another value. That's good enough. And then we also get what the signal number was, and pretty sure it should be the same thing almost all the time because we're handling SIG-SEG-Vs, but I think we got a couple other things. In case, we create a file name for ourselves that should be unique. We then open it. It's read, write, create, so that it's going to create a new file for us. We then do this little memset. We build this string for ourselves, and we print it out. And basically what we're doing here is we have the past 32 fuzz tests. Hello, everybody who's just joining in. What we're doing right now is we're going through we're basically recapping the past 7 episodes. So we've got this, we loop through, we dump the past 32 elements that we've fuzzed and created, and we just dump them out to a file, and we exit. Relatively simple. And the third thing that's important is this test function. And what this is doing is this is actually loading up that buffer which holds all of our test cases. And again, this is relatively simple, right? We just have this buffer right here that we've allocated ahead of time. We're then going to just index into it. We then just do a str_n copy and we dump memory into it. Super simple, nothing very complicated about it. That's all it is. We compiled that, and then we use C types to load it. Then to actually do things, we've got a few different pieces of code here. I believe the first one that is important here is our test harness. And again, it's relatively straightforward. We load that module we just showed you, the ctypes test.so. We then call a tester.init. That was actually, what am I doing here? There's no reason we can't have both these open. Vim ctypes test.c. So we loaded this module. We then call this init. So we get our nice buffer allocated. We then call gen init. So that is, oops. Gen.py. There we go. And gen.py is the Python side of our test harness. And what this is doing is this is actually generating the test cases. So gen is the generator for a fuzzed Python input, whereas tester is the actual test harness in ctypes. So we call this gen.init. And this is relatively simple, right? We initialize it. We've got a set of functions we're going to skip over. These, I think, info captures standard in, show config prints out a bunch of junk. I don't remember what these two do. Basically, they're functions we know are going to cause problems for our fuzzing, so we just skip them. Then what we're going to do here, and we're going to use this kind of awful code here. Basically, what we're going to do is we have a set of callers. And the way that this works, and this is a list comprehension here, right? So we're going to, for every object in the dir, so we call dir on np, and we declared np up towards the top here for numpy. So it's a numpy module. So every object in the numpy module, if it is callable and it's not in this skip. So we don't want things like, so if I do Python import numpy as np, so there's a bunch of stuff in here. And there's things like zeros. Is this going to be one of them? Oh, they misspelled zeros, I guess. Jeez, and I can't type, apparently. Oh, I guess that is a function. Well, so how about an easy example, right? So we have np.doc. This is just the doc string for numpy. We don't need this. There's no reason for us to include this in our fuzzing, except possibly that it's a string that might do something useful. So the reason we're not including this, though, is because if we included it, the rest of our code doesn't work. We assume that we want to fuzz functions, not strings, so we're just going to grab all the functions. So this right here is going to grab all the functions. This creates a tuple for each of the functions, or everything that's callable, not necessarily a function. And the first thing here is a prefix for it. Because we're just initializing everything, there is no prefix. And then we have this np.object. Works fine. And then we call a global types because up here, oh, we're in the wrong one. That's why it didn't work. Up here, we've created an array for both the list for both the callers, types, and then there's args up here, which we'll get to in a second. So we then initialize types. Basically, everything that we can initialize, we're basically just going to dump in there. And this is, so we just started streaming about 10 minutes ago for tonight. We're just recapping the past 7 streams worth of stuff, talking about our Python exploit. So we've got this init function, we initialize things, and this is going to set up things for generate. So let's come back over here. Oh, oops, this one. So for each test case, we're just going to loop through here, we're going to run some test cases. We generate a new test case, we use tester.test to register it, We then use exec to execute a single test case with only that Numpy module in the globals for it. And then finally, we register it. And if everything works, we go on to the next one. Relatively straightforward. So the reason we're doing this gen.register, this is a little complicated. So give me a second here. So we have the generate, which is going to create a test case. And again, it's relatively simple. We create a input ID to randomly name a function. Because what we're going to do is we're going to create a function. Then we're going to pick something, one of the callers, which are functions we know we can call. We then decide if there is, so the defer is the definer. Basically, as we go through, we'll add new functions that we might want to call. So for example, 3, is that where we're? Yeah. We might do a is equal to a numpy.array. And a has a whole bunch of new functions on it. So a numpy array, if we did this properly, oops, if we properly initialize this, then our numpy array has a number of member functions that we might want to fuzz and we want to call. For example, I don't know, we might want to call this getField function or this setField function, which are not part of the Numpy module. We can't just get to them. We have to first initialize this and then define it. So what we've done is, if we've defined something, we've gotten a new class, then we might want to create a new way to call it. Basically, we just loop through, we create this, then we create a set of arguments for our function. So we've picked one of the things we can call at random. We're then going to set some random number of arguments, 0, 1, 2, 3, or 4. And for each of those, we're going to call one of these functions. And basically what we're doing here is we know that we can create a function that will create some object of some sort. We're basically just going to randomly shove them in there, set up the args list, and we're going to join it all, and we're going to return it. And so this is, you know, a little bit cracklib. So we have this, and if we come into Python, so here are some crashes that we got. And for example, OX53. Here's what one of those looks like. Basically, it's relatively straightforward, right? So the caller that we selected here is this right here. We want to call the hash function on whatever this returns. And this was previously set up to use int as buff to return this thing. And this has several things. And the reason we do it this way is because it's relatively straightforward, and it makes it easy for us to create arbitrary objects and still have a similar interface for our fuzzing. Because we're just trying to generate these arbitrary complex objects. So having a simple interface, here's a single function with no arguments that we call to create an object of some sort that does something. And that's all it is. It's relatively straightforward. It creates things like this, and it calls them. That's it. And then up here, there's also the register function, which is if this did not cause a fault, if Python went through, there were no exceptions, everything was kosher, then we want to register this as something new. If it worked, then if it creates a new class, we want to add that as something we can call functions with as an argument. Then we also want to randomly just add it in anyway, even if it's something we already have. And the reason we're doing that the reason we're randomly adding in more stuff is because, well, maybe, one array isn't large enough to cause an issue, but another array is. So sometimes we might want multiple arrays in there. And that's the reason we do that. So let me see here. I think that's about everything about the fuzzer that's important. We did write, in addition to this, a pretty simple projects Python. Where's our shell script? Is it wrapper.py? Yeah, we wrote some pretty simple just wrapper functions. The reason for this is, if you noticed, we didn't have any functionality to try and strip out anything, really. So what happens if one of these functions doesn't crash, but it takes forever to run? So basically the way that we ran this was we had this little wrapper function that would keep starting up this process. It would keep running it. And then in a second shell, we would just kill them all. And the reason for that is because if we kill them all like that, then we'd kill all those processes. I believe we stuck with about a minute timeout. So this fuzzer would start, it would run, it'd fuzz for about a minute, and then we'd kill the process and start over. And that serves two purposes. One, it lets us kill processes that are hung for some reason. Like maybe we've accidentally told it to, compute 2 to the 64th. Because I think that's a thing that our fuzzer can generate. Because we can call, what was it, 3? So we could, if we did 2 to the 64. This is never, it might finish, but realistically, it's probably not going to finish. Because this is a massively complex thing to try and calculate. Like it's calculating a massively large number. It's going to sit here, it's going to chug, it's going to chug, it's going to chug. That's never really going to finish. And we don't really want our fuzzer to sit here forever computing that. So we set this timeout, we kill everything regularly, and we start over. Super simple, straightforward. One thing to note here, we're not saving off any of our state when we do this. And that was for two reasons. The first was saving off state adds complexity, it adds infrastructure we'd have to build, it would add a whole bunch of extra stuff. And the plan originally, if you go back to episode 1 of this series, was basically we were going to build all this, we were going to see where we got to. If we got any crashes, great, we take a look at them. But the plan was originally that we were going to set this up, we were going to run it, and then we're going to go back and add a whole bunch of additional functionality. Things like saving state, a better test harness, we'd improve on this. However, I think it took a grand total of about 45 seconds until we got our first crash, so we haven't gone back and fixed all that yet. We're still operating at this dead simple setup for fuzzing because that's all it took. All it took was a simple, we just list all the functions, we then just randomly jam them together and call things at random out of them. It's nothing complicated at all. And we got crashes. So I kind of showed this earlier. Where were we? Yes, in here. And let's move this over so we're not doing this. So in addition to, oh yeah, that's right. So in addition to all of this, we've got this, I believe it's classer.sh, which it's really just super simple. We want to classify all of these crashes too. And in order to do that, so we have this input that we think should cause a crash. And what we need to do is we need to do some initial triaging. In total, I think we got about 7,600 crashes. So we're going to EC2. Yeah, we got a ton of crashes here. 7,596 crashes in total. And this was from, I think, running for about a day or so on a EC2 instance I threw up. These are all the crashes we got. Awesome. But that's way more crashes than I can go through manually. I can say, okay, we're gonna look at this one. What is this one? Okay. Next one. And go through like that, and go through another, and another, and another, and another. Actually, this right here is the part that crashes. We also print out this last one. That's a bug in our test harness. This is the one we actually care about. In any case, this one is triggering this as type null deref. So this is one of the crashes that we found. But in case, we put together, again, this super simple script. We're just going to go through, we find all the crashes we have. We're then, end in pi. We're then going to execute gdb-x, and we have this ripclasser.gdb function, or file. And again, incredibly simple here. Python rip classer.gdb. Incredibly simple here. All we do is we set logging on. First we run it. We set logging on. We then print out the current return address. We show the arguments and we quit. Incredibly simple. It's just going to go through. It's going to get all this stuff and then it's going to quit. And this generates something like this. And again, this right here, massive amount of text, but we can then process this a lot easily. So for every single one of those crashes we think we have, we got a line kind of like this. Basically, we have what current RIP is, and then we have the list of arguments for it. And so this tells us what was the function, or what was the file that caused the crash, and what RIP did we end up crashing at. One thing that's important is there's some other code in here, repro code, I believe, to verify. Oh, nope, that's not it. Trying to think here. Unfortunately, over the course of all of this, things got a little bit messy. I did not do a particularly good job of keeping my workspace clean. Among other things, if we were doing this for real, I should really have, a nice repo to hold all this in. I should be, keeping track of things. I shouldn't have, 4 different tests that are for different things. But, if it works, I'm not going to complain too much. Yeah, so this is what it does. Basically, we go through for a given test case, we check to see, does it reproduce? We assume that this is going to tell us a number, we try and run it, we just see if it reproduces. And then I believe we have something else in here which actually runs through it. Well, that's the, actually I think it's this. Yeah, I lied. Oh, it's this. So we're going to go through, we're going to find all of our crashes. We just do some super simple here, make sure that it actually includes a crash. We then try and reproduce it. If it reproduces, we're going to copy it over to a new directory. Hello, Glass of Sound. That's it. Relatively straightforward. We go through and we didn't do it here, but there's a second version of this script, which I appear to might have lost. And that actually takes us from the basic stuff to, we've now also created directories for each of these with RIP to classify them. It makes it relatively straightforward to go through. Rather than having to take one of these at a time and try and figure out what it is, we have, so OX4E05F3. This there's only one here, but we know that this is the only input that we found which had this unique RIP, or 7 many Fs. This also only had one. But we can go through and we can see, okay, so this is how this one was caused. That's interesting. One thing that is somewhat important here is we actually haven't gone through and triaged all these crashes yet. This one actually looks different. So I don't actually know why this one crashes. This is one of the ones we have not gotten to triaging yet. If you look over here in the notes, a whole bunch of these we never triaged. Because once we went through, so if we actually come over here, so these are the notes that we had. We went through on, there's a few things we spent a long time doing. One of the big things was, after we did the first several of these, we went through the first several manually, and we said, here's what's going on, let's take a look at it. And so all of these are, they're crashing in the Python code, and I believe they're all crashing because of this int as buffer function. And int as buffer is a, it's an interesting function, and it's one that if I was writing Numpy, I wouldn't include. Int as buffer. What do I want to do here? I believe, yeah. So let's say I have st is equal to many a's. I want to get the address of st. One thing that's important here is there is this amazing function called id in Python. What is id, you may ask? id returns the memory address of any object. The reason they do that is because I think the Python developers kind of assume that if you can run arbitrary Python and call a function like id, you could probably do something like, I don't know, import os.system/bin-sh. Right? Makes sense. Like, if you can call any function, then you can do a lot worse than find out a memory address. It makes sense. But when we're doing exploitation, it makes things a lot easier for us. So we have this address here. Now I want to do np int as buffer, int underscore as buffer. We're going to take that address, and I believe we're going to take, let's do a bunch of bytes. Okay. What does that do? So int as buffer is a Numpy function, an undocumented Numpy function, to take a Python integer and read some number of bytes out of it and return it as a Python buffer. It is literally just read bytes out of memory. Like, give me an address as a Python integer and read a whole bunch of bytes out of it. I literally have no idea why this function exists. There's been some, speculation that this is related to C types. Like, Numpy is designed for, high performance stuff. I need to run a whole bunch of stuff. And sometimes I'm going to write C types to do that. Like, I want to write some C code because it's going to be faster. The problem with that thinking is, why is this in the Numpy library and not in the C types library? But, you know what? I'm not one of the developers. I'm not going to argue too much. We've got a whole bunch of crashes related to this because, well, okay. What if instead of doing, 40 hex bytes, we do that many bytes? Oh, well, we cause a segmentation fault because we're going to read outside of the bounds. Like, we're going to read into an unpaged page. Oops. So we've got a whole bunch of crashes related to that, which is what most of these were. And then we got into some of these. And when we got into these, basically what happened was we knew we were getting heap corruption. Okay. If you're getting heap corruption, it can be tricky to figure out exactly what's going on. And the first thing we wanted to do was to set up ASAN. So if you're not familiar with it, ASAN is what do they call it? A compile. It's a bunch of checks included as part of Clang. It's called the address sanitizer. The basic idea is most exploits, I think it's probably still true, most exploits are related to what's called memory corruption, right? That there's some sort of a region of memory. Ooh, I can do this in Paint. I can try and do this in Paint. Let's see if I can do this in Paint. So there's some sort of a buffer in memory. Oh, I need a pen instead. So there's some sort of buffer, in memory, and we're going to write into it, except instead of writing into it, we're going to write over here instead. It's a buffer overflow. We went outside of the region that was actually part of the buffer. Pretty simple, right? But yeah. So the problem is, especially when we're doing heap exploitation, we might write, where are we? Sorry, the mouse ends up on the wrong screen, and where are we here? So we might write over here. We trash all this memory. It's all trashed. It's awful. But when we crash, it might not be until this region right here is freed. Or it might not be until after that when this stuff is actually read from. I don't know. It's not going to crash when the actual memory corruption happened. It's going to crash some other time when it's read. For stack stuff, it's a lot easier because how the stack works, right? it's kind of contained to the function that it happened in. So it can be easy to look at that crash and say, oh, here's what happened. Whereas with heap corruption, it might not be contained. Oop, that's the wrong one. I want to get rid of this window. It might not be contained to the same function. So that's the basics of it. So we wanted to get ASAN running, because if we did, it's going to be a lot easier. Instead of having, oh, someplace in this we caused a crash, we're able to say, here is exactly where we first wrote or read out of bounds. The problem is we spent about an episode and a half on it, I think, trying to get Python and Numpy to build with it. And I believe if you go through the comments and look at it, we had a bunch of people help out and trying to get it working. But the short version is, on stream, we never actually got it to work. So I, completely so part of the problem is I got it halfway working on one setup and then rebuilt the machine I'm using for streaming and never bothered to get it working on there. And in any case, we never got the ASAN stuff working. There's at least one person, if you go back in the videos, I'm trying to remember who it was. I believe it's on episode 4 or 5. Where are we here? I want to actually go to the video. Yeah, so properties. Yep. So if you actually go to, it's episode 4, Adamowini went through and he actually got it to build. I haven't tested this. I don't know if it works. But it looks like this works. I know we also got a ton of help. Yeah. That's all of that. That's the ASAN stuff. Wow, we had a whole bunch of people show up. So go through the questions. Any plans for CTF? The only CTF that I'm currently playing in is the Labyrinth stuff. I started working on that over the weekend, trying to get through it. Unfortunately, for the next week or so, I'm traveling and won't be able to participate much in the Google CTF coming up this weekend. If you have the time, I totally recommend it. It should be interesting. I also recommend the Labyrinth stuff. They're both pretty fun. And as far as Disconnected, thanks for dropping in. I will definitely try and post something. So assuming we have enough time, the plan is to, after we get through all of this, go through the code and actually try and fix this. Because it's not enough for us just to have found this bug. Ideally, we also get it fixed. Because, we're good people. We're going to fix all the bugs. We're not just going to find them, write an exploit on stream, and then not tell the developers. That seems at least a little bit irresponsible. So the plan here is, once we go through all of this, we're actually going to go through and we're actually going to look at the code and try and fix it. So ideally, we're going to end up at the end of the stream with, here is a patch that we can submit to the developers to get it fixed. But going back to where we were. We tried to get ASAN working. We did not get ASAN working. We went back to triaging it. We used what I'm calling janky ASAN. I'm not sure where that ended up. Projects, Python. Oh, it's an ASANer. And what this is basically what we did was we set up we used a malloc hook. Basically, we set up, sure, delete it. Pretty simple. When this .so initializes, we set up a malloc hook to instead use our new malloc. And new malloc, super simple. We just use mmap instead of malloc. Again, straightforward, pretty simple. What we're doing here is we're saying, instead of using malloc and having everything right up to each other, we're going to create a buffer with a guard page. Again, relatively simple. What this is going to do is this is going to protect us from a lot of problems. One thing that is very important, though, that was pointed out in the comments. Come on. Sorry, my YouTube is loading a little bit slowly here. I believe it's on 5 here. Well, I'm not seeing it, but at least one person pointed out that turns out AFL includes this. Not as part of the mainline stuff, but AFL. Yeah, this right here, the lib dislocator, it's part of AFL, includes all of this functionality. As an SO, we can load the exact same way. Turns out, probably should just use this instead, but writing the code was pretty straightforward. It worked. We got where we needed to be anyway. So we set this up, we ran through, we did some more test cases. And then, well then, we found the bug that we ended up landing. What is the bug we ended up landing, you say? Well, it turns out that actually, let's start by going in and actually taking a look at what the exploit we came up with was. So the exploit we have here, I believe it is sploit.py? No, it is sploitorig.py. What is this? So we found that there are two functions, the getField function and the setField function, that turns out they take in, so they are members of a Numpy array. So we have n up here, which is a Numpy array that we've initialized with ABCD as a string. And both the getField and the setField, so the getField function to start with, it accepts two arguments. First, a data type. In this case, we are using int64 because that's a 8-byte character that's relatively easy to read and write. And then it accepts an offset. It does not check the offsets. It just takes a Python integer and it adds it to the start of the array and it reads some bytes for you. Pretty simple, right? Turns out we have an arbitrary read because of that. We can read basically any memory address. But the trick here is that we can't actually read any memory address. So the short version here is that it is bounded to a 32-bit integer offset, a signed 32-bit integer offset. So unfortunately, that means that we can only read 32 bytes ahead of or behind our array. Not 32 bytes. 4 billion bytes? 4 billion bytes ahead of or behind, which on a 32-bit system means we can read all of memory. On a 64-bit system, like we're using here, it means we can read only a very small segment of memory. So we can read and write it though. That seems good enough. So the exploit we ended up coming up with, this took, I believe this is episodes 6 and 7, are going through and landing this. And this is a little bit complicated, although not terribly. So we have a buffer here that we initialize. We have our NumPy array. We get a pointer into our heap, and the reason we're doing that is just so we have a good place to start with. Then we have this object def. Basically, we know that the definition for something is going to be at this offset. We then get a function pointer using that. And then this right here, what am I doing here? Control AZ. Oh, that is not what I wanted to do at all. Sorry about that. Let me just get this all fixed back up. Okay, this was 4. Well, I guess we're gonna scroll this way then. So this code right here is, oh, and of course my highlighting isn't gonna work very well, is basically direct output from Wropper. So Wropper was Wropper was this thing. It's a tool. I don't know, like it's a tool. It's a thing. Somebody wrote it, and one of the functions you can do is you can tell it, I want to generate a chain which does a thing, and I believe it has two options: either pop a shell or to memset some memory read write execute. In this case, we just popped a shell. In our case, we had to fix up a couple things here. So we've got this code right here. Basically, we're gonna bash a gadget in there, so we had to hop over it. But let's talk a little bit about what happens here. So we have our ROP chain, and what we actually end up doing is a little bit complicated here. So what we do is we create a Numpy array with our ROP chain in it. Then we get the address to it, because of course, for a Numpy array, there's also this ctypes.data member, which is literally just the memory address of the data for it. So not the full object, just the data. Awesome. And then we create this crash string. And not to go into too much detail, if you're interested, look at episode 7 of this. We spent basically the entire time really hammering in how to do this. But what we're doing here is we're searching through the heap for something that looks like the table for how to handle a string. So the way the Python objects work, there's going to be a table in memory, which tells us, here's a string, how do I print it? How do I free it? How do I, get bytes out of it? There's a table in there with a whole bunch of function pointers in it. We use that and we bash one of these pointers. So first we find that on the heap. The reason we're finding it is because with ASLR, this is the address in GDB. With ASLR, everything but those last 3 characters are going to, everything other than the last 24 bits, 16 bits, 12 bits, however much that is. Everything but those last several bits are going to be randomized, so we can't trust them. This, however, will work. We know there's a certain offset we have to be, and then we know what the value we're looking for's lowest 12 bits are. So we just search for that, we find it. Again, relatively straightforward. We have this overwrite that we're going to use. And we've got 2 gadgets here. And I'm not going to go into a ton of detail about how this works, but we do this swap, basically. And what we're going to end up doing here is we have a first gadget. And if you're interested, definitely go watch this episode 7. We go into a ton of detail searching for these gadgets. But we do this swap. We write that in. And then we print out our crash string. And what it does is, if I remember correctly, it's going to take this pointer. So we've written in this gadget, which is going to grab our pointer, it's going to use it, and it's actually going to call up here. And we use these 2 gadgets here to set everything else up and actually swap back, I think. Again, if you're really interested in how our ROP chain works, definitely go watch episode 7. We go into a ton of detail about how it works there. So, that's the exploit. And if all you care about is the offensive side of things, this might be all that's interesting tonight. That's the exploit. It's a relatively quick explanation of how it works. Now what we're going to do is we're actually going to go through the Numpy source code. And we're going to take a look at it. And assuming we have time, we're going to actually give it an attempt at trying to fix this. Oh, wow. I forgot to fix all this stuff at the start of the stream. Numpy overview and patching. And let's move you over here. Ooh. Properties. Oh, yeah, that's good enough. And then we have, let's fix this. So we've got this right here, and we're gonna change you to. So one thing that's important here, our next stream is not until Wednesday 6/21. I will not be streaming on this Wednesday or next Monday. I'm traveling for both of them and will unfortunately be on an airplane when I usually travel, or when I usually stream for both of them. So no streaming for me from 30,000 feet. I don't think the airline would appreciate me eating all their bandwidth for that, or my neighbors for talking like this the entire time. So, what are we doing for the rest of today? Well, I wanted to move this down a little bit, not my entire thing. There we go. Let's actually go take a look at it. Where are we? So we already pulled down Numpy, and this right here is the current Numpy source code. And at this point, things that are important, we've gone in here, we have NumPy. We have already set up a tags file. So let's go find our grep rn get field. We're just gonna go find the function. Ooh, a little bit more than I expected to see. So, well, we can do this the easy way. Really? Not found. So what I was trying to do there was I was trying to take advantage of that. I'm sorry, I'm blanking here for a second. Tags file that we created to use that. Having said that, though, we can actually see here. There's the methods, the get field here. So let's actually open this real quick. Oh, really? Does this Vim not support that? 2610, I believe. Yeah, so here we're setting up all of these functions. So these are the functions for these are the array methods. And what we care about are get field and set field. So we have array get field. Seems pretty simple. What does array get field do? So we have a keyword list with dtype and offset. We then do a parse tuple and keywords. PyXD decref for dtype. And then we're going to call pyArray getField for dtype offset. Okay. What does this do? Get a subset of bytes for each element of the array, steals reference to type D must not be null. So we set up an offset. May have objects. Check that we are not representing memory containing objects. Not reinterpreting memory containing objects. Okay. Don't think any of this matters. New from desk enter. Again, I don't think this matters. So type D is the array description. So that's that int 60. Let's pull this up again. 3, 2, 6. Projects, Python, exploit, exploit, orig.py. So we did this, remember, we call np get field. So the NumPy array is self. That first argument there, the type D, is this object describes what we're looking at. And then offset is an integer offset. Seems straightforward enough. So we have a new from description int. Okay. If that is null, we return null. Otherwise, we're going to do code for this. Okay. Generic new array creation routine. Internal variant with calloc argument for pyArray zeros. Steals a reference to description. On failure or description subarray, description will be decreft. So this seems simple-ish. So I think the important thing here, we have a pyArray object. And a pyArray object is a pyArray object fields, which is this thing up here. So a pyArray object field. It has a pointer to the data. It has the number of dimensions and the size in each dimension. So unfortunately, they don't actually have what I was really hoping for here was that a NumPy array would have a very clear value here that we could say, here is the size of a NumPy array, and that's all we care about. As long as it's in the right thing, we're good enough, we don't care. But it seems it's not quite that simple. So we have data. We have the size in each dimension, also called shape. then we have this thing. Where are we? So we have the number of dimensions, the size in each dimension. What is a stride? The number of bytes to jump to get to the next element in each dimension. We have a base, we have a pointer to the type structure, and then flags. Is there an easy way to do this? Are we super lucky? So import numpy as np. N is equal to np.array, abcd, dir n. Oops. Well, that's okay. I was thinking this would be simple, but I don't actually know how to do this, right? So I want to know how many bytes is this thing? 2 bytes. So I guess that works. So however 2 bytes works, it has to be able to calculate how big this thing is. So let's walk back here. Where is 2 bytes? How on earth do you work? So 2 bytes is going to take a pi array to string with an order argument. Okay. So it turns out that there is in fact already this nice handy macro that does exactly what we want. So we're going to take this macro. We're going to go back, and we wanted get field. Where were we? Go right here. We have our get field, and we're just going to be super simple here. We're going to say that if offset is less than 0, or offset is greater than whatever this macro is, return null. Again, super simple. We're just saying, if thing's too big, just return 0. Oh, so we did that. We also want to do set field. We're going to do the exact same code here for set field. So unfortunately, we're going to call get field before we do a copy object. All right? So let's actually come back here and make sure we're correct. No, we're not correct. So we have this right here, which did all of this work to get us into this function. So we have pi array get field, and we have array get field. Oh no. I think it's good. So we want array set field. Again, same, pretty simple code. If we're outside of the range that we should be able to read and write to, we're just going to return null. And now let's see, are we? How lucky are we? So to start with, we're going to come over here, cd projects python exploit mkdir patch cd into patch, and we're just going to write a test case here. And so this test case, numpy get field set field. Okay, So this right here is the example code from the documentation for using, oops. So this is the example code for using get field and set field. Let's actually leave those in. Import numpy as np. So this is the example code. Sorry, I kept trailing off there. This is the example code for using get field and set field out of the scipy numpy documentation. We're just copying this straight up. And so the reason we're doing this is, again, numpy is supposed to be relatively performant. That was not big enough. So if our test case takes too long to run, like if our patch ends up, quadrupling the throughput of this, well, maybe the security isn't worth it. I think it's worth it, but somebody might make an argument that it isn't. So, time Python test case. This runs in about half a second. Let's actually up this some more. So this should take about 20 seconds, I think. That's the way that math works, right? 8 seconds? Something like that. Yeah, look at that. About 8 seconds. I can do basic math. Yay! So, we have compiled our Python. We've done stuff. Sudo python setup.py install my password. It's not actually my password. So what we're doing here is we're rebuilding NumPy with our patch in place, and assuming that everything works properly, this is going to install it to our system. Now, assuming that everything works properly. Do we see a detectable change in time? 1, 2, 3, 4. It is actually faster. Yay! And that's it. So if we do this, we should be able to do Python import numpy as np, n is equal to np.array abcd, n.getField np.int64, comma ox many thousand bytes. Oh no! Ooh, no. For some reason, our source code is causing other problems. Interesting. Import numpy as np. So we're actually, our exploit is actually causing a, so we're running into this other edge case. There was some stuff we ran into previously with it that under certain situations, like it's a really fragile exploit. So dir np, I want np, this is way too much text. np.version, right? This is what I want. 12.1. Well, this isn't right. I want 1.14. Why did you not give me 1.14? So I want to run this. Okay. How do I build you? Build -j4 install. This will not compile, but I can use, okay, I can do that. Python setup.py -- in place. Oh, build. Oh. It helps if I can type properly. What? So we're now building this in place, apparently. Apparently that's an option we can just do. See, reading all that documentation would sure be nice before we did all this work, because trying to get that to work was kind of a pain in the ass on episode 4 or 5 when we were trying to build it with ASAN. We were in a, for anybody who did not watch that, we were in around and around and around and around and around in circles. Because, yeah, getting this to build with ASAN was a massive headache. So, again, if you're interested in that, there's many hours of me bashing my head against the keyboard and getting help from Cassiano, and I believe Disconnected was helping, and Animawini, and all these other people. Like, tons of people pitched in, tried to get it to work, we tried to get it to work, we tried to get it to work, and eventually I just, this is taking too much time. We're going to go do things the hacky bad way instead. So now we wait. Come on. Unfortunately, the compilation time for this is a little bit on the long side. It's definitely longer than I would like it to be, especially for doing things on stream, so. Yeah. If anybody has any questions, feel free to throw them out there in the chat. Hopefully I did a reasonably good job of describing everything as we went along here. Because at least my plan here is that basically to put together a patch here, submit it, and include a link to this video as a description of why they should be accepted. Because this video probably does a pretty decent job of explaining that, yeah, probably not the best idea to have these problems. So, come on. Just a little bit farther. You're almost there. You really are. Actually, I don't know if you're almost there or not. I'm completely lying when I say that. So, that's odd. If we didn't end up with the right stuff... Did we actually throw this at the beginning of the stream? I'm a little bit confused about how this happened. Like, I'm a bit confused about how we're running into this error when... Pretty sure we had, towards the beginning of the stream, we actually landed this. So we've done something to change our system, and unfortunately I'm not quite sure what it is, but I'm prepared this time, and we know how to reset things. So I guess while we're waiting here, how was everybody's Monday? Anything exciting going on? I'm kind of guessing it's going to be kind of quiet today. Looks like we've got a little bit lower turnout than usual for the video, for the stream. My guess is a lot of people, once they saw the offensive part, they might not really care that much about the trying to patch things up and get it fixed. Because, at least somewhat, unfortunately, the offense side of things is exciting and sexy and fun to watch. You get to break things and, you know, kick things, and it's cool. And when you fix things, well, you sit here and wait for things to compile. It's not necessarily the most amusing thing to watch. Now, hopefully hearing my soothing voice talking about things is, Thanks. Oh, there we go. Good, way to make up for that, but, import Numpy as np. np.version. There we go. We now have our version built with our custom checks. We have NumPy array ABCD, n.get field. We're going to call this with an np.int64, and we're going to call it with many bytes. Too many bytes, apparently. Yeah. And that is our stuff, which should be working as intended. So if we do 4, we return a thing. 0, we return a thing. Or 1, we return a thing. 5, we stop returning a thing. We had 4 bytes. It's going to give us 4 bytes. And I'm not quite sure what it's returning. Like, it's still going out of bounds a little bit, but, you know, it's still working reasonably good. So we do this, and not thrilled with this. Like, it would appear that, definitely looks like this is not working quite the way that we want it to, right? So we're still going outside of the bounds of what we want it to do. But how much do we care? So one thing that's important here is we need to go in here, and for whatever reason, our stuff did not exploit patch test case. We're gonna run it. Oh, we need to do time bang bang. Time with an E. Tim is not a thing. So, well, thank you, Nicolo. I'm glad that you're enjoying it. So basically what we're seeing here is if we were doing exclusively operations with get field and set field, it adds about 10% overhead to have our check. Well, we don't actually know that for sure because we're doing this with the, so that's with the check. And where is, oops. So if we instead comment this out, and we comment out this one too, we come back down here, we're going to build it again, and hopefully this time it builds much faster. So hopefully it, you know, only rebuilds the multi-erased. Yeah, there we go. Much faster this time. How long do you take? So realistically, we're adding, what is this? Because it was 8.4, 8.5 seconds with our check, and 8.3 without it. So we're adding, like, what is this? 3% overhead, 4% overhead. Realistically, I think that's perfectly reasonable to not have a blatant buffer overflow in your code. Like a less than 5% increase in time seems perfectly reasonable to not have your code be completely broken. So yeah, that's all it is. Like, again, this is super simple, right? All we did here was we found the function that's calling this. We're adding a check. One thing that's worth noting is our check is still broken. It's not doing things quite right because we can still do an out of bounds read and write. We're just making sure that the start of it is within bounds. So ideally what we would do is we would check that the start plus the size is proper, but I don't, well, you know what? If we're going to do this, we should do this right? Let's do this the right way. So cd numpy bang vim. Okay, so we have this. We also have a description. So how do we do this? So this is accepting a pi array description. What is a pi array description? Oh, this is many things. Oh, that's easy. There's an L size. Oh, oops, did not mean to do that. So there's an L size. So we want to make sure that not only is... where are we? Array get field. So not only is... So we want dtype L size? I believe that's what we wanted. Is less than 0. And the reason we're adding it beforehand is because like we want to check for the overflow case, and I think this is a little bit easier than trying to do it manually. cd ... Man, it's kind of crazy that code just works. I'm not used to my code just working like that. Import, like especially my C code where I'm just like patching random code I don't actually understand that well. Not used to it working quite that well. We want to do dot array. So if I do n.get field np.int64 0, it still works. Interesting. Vim numpy. Oh, it's because we're commenting it out still. That's not what we wanted to do at all. Does not help if our patch is then immediately commented out and it doesn't actually run. Import numpy as np, n is equal to np.array abcd, n.get field np.int64 0. But if we call it with an int32, it works. Pretty happy with that. Like, that seems good. And I believe that if we take this value right here, we get ABCDE, ABCD. And we should see similarly that if we did this with offset 1, it has an exception. So again, pretty simple, pretty straightforward. And if we run this right here with our patch, we take cd python projects, cd projects numpy. So we have that time there. We're going to numpy core. Oops. What was this called? For source multi-array methods.c. And so when we comment out our patch, so I don't actually know if the developers care that much about performance. Like, it's entirely possible that all of this work to make sure that we're relatively performant doesn't actually matter, because the developers might just not care. Like, it is entirely plausible that they're going to say, oh, no, you totally fixed a bug, that's good, congratulations. But I kind of want to have this number to say, look, our very naive patch, it adds... what is that? 8.696 divided by 8.890. I did it the wrong way. 8.890 divided by 8.696. Our patch adds 2% overhead if you are doing purely get field and set field operations. That's a trivial increase, and it fixes a bug in your code. It seems very straightforward that this is a patch that should be accepted, because it's 6 lines of C. All it's doing is checking our sizes. I'm of the opinion that this is something that should go through pretty straightforwardly. So my plan here is to basically submit this, if not tonight, then tomorrow, get it reported to them, hopefully get it upstreamed and fixed, and have everything taken care of. So yeah, I think that's about everything for tonight. I know I mentioned this at the start of the stream, when Muguntin asked. So for those of you that are interested in the CTFs, we have Labyrinth, run by Palo Alto Networks, that is currently ongoing. And then this weekend is going to be the Google CTF. Both of those, I think, are worth playing in. Again, assuming you have the time for it, because both of them are probably at least relatively decent time commitments. So pulling this up here. So Labyrinth is currently ongoing. It runs for a long time, though. It runs through July 23rd. So don't feel any push to do it. There are prizes that are first come, first serve, but like, I'm definitely taking my time for it. I'm trying to record the progress I'm doing on it, because at least my thought on it is I'm going to go through, I'm going to play it, I'm going to hopefully get through all of it. And then after the fact, after July 23rd is done and the competition is over, I'm going to actually post those videos and people can watch me solve it. Because it's one thing for me to sit here and poke at stuff on stream. It's a little something different to do the same thing when it's problems that I haven't posed myself. All this Numpy stuff was stuff that we came up with talking about. Whereas the challenges in a CTF are things that I don't control. I can't take shortcuts, I can't work around things, I have to do whatever constraints there are in the competition. So getting a chance to watch that may be interesting to people. At least that's my plan for it. And then also this weekend is going to be the Google Capture the Flag. Last year was apparently a lot of good challenges. I don't remember playing it that seriously, though. That was part of the time when there was a whole bunch of flux with the CTF teams that I was playing with, and didn't really participate with anything. And unfortunately, I'm traveling and not playing this very much. I may try and do a little bit in the evenings, but we'll see. But this weekend, do recommend giving it a try. Other than that, the following weekend, there's apparently a couple of competitions going on. I don't know anything about them. It may be worth playing, it may not. If you have thoughts on it, please leave a comment here for other people. That'd be great. Especially if you played in either of these previously, and I believe that's all that's coming up. There's also the Nuit de Hack Finals, if you happen to be in Paris, France, and already qualified for it. Other than that, Secu Inside in a couple weeks. That I suspect is going to be a lot of fun, and I plan on trying to play it at least a fair amount. Unfortunately, that's not a great day for me. I have some other plans, but we'll see what kind of progress I can make. Yeah, it looks like there's going to be quite a few events throughout the summer now. There's Poly CTF, which I vaguely remember from last year. Maybe. Yeah, I think it's one of the Italian ones. There's the Shaw thing. There's also going to be DEF CON Finals if you're going to Vegas for it. You'll either play or hang out in the CTF room, watch things, heckle, do things like that. There's a fair amount. Unfortunately, the summer and the fall are kind of the slow time for CTFs. Most of them are in the spring. It has a lot to do with the historic base in college students. So the fall, the teams get together. The spring, they rate competitions. So apparently I should give a huge try for Poly CTF, because apparently one of the organizers is watching my videos. So I will definitely make sure to give that a try. Again, unfortunately, I think that weekend I also have stuff going on, but I'm going to definitely try and give it a try. At least that Saturday, I think I should be able to give it a good effort, but we'll see. Hopefully I'll get a good chance at it, and it sounds like it should be a lot of fun. So thanks everybody for tuning in today. I think it's about all that we have for today. It's going to be a pretty short stream. It's only been about an hour and a half now. Well, I guess one more thing for people who've stuck around for all this time. I think the next series, so we've done all this Python stuff. We've basically wrapped it up. We have a patch to push in, report. We could go a little bit farther with it, go through, add, state to this, add a backend and all of that. But realistically, I'm not sure how interesting that is. Like we've done some basics on fuzzing. We've taken a look at things, and let's go back over to this. But kind of just hammering back and forth on this. Like hammering on Numpy, I don't think makes a ton of sense. So at least for now, I think putting this to the side and maybe coming back to this at a later date is a good idea. The next series that I think we're going to do is we're going to take a little bit of a divergence, or what's that word? Detour, maybe? So most of the streams, so we've been doing these for about 3 months, I think? Something like that? 3-4 months? And most of these have all been focused on exploitation. So here is some sort of binary. How do we get, first, how do we find a bug in it? How do we exploit that bug? How do we land it? And while that's all interesting, it isn't the entire problem. The other side of it that's actually quite interesting too is what are we going to run? So I think the next little series we're going to run through is some shellcoding. So we're going to actually try and write some interesting looking shellcode. At least my thought on it is I kind of want to design some shellcode which is a valid image that will run like pop a shell or something. At least that's my thought on it. I don't think it's going to be super complicated, so hopefully that's only going to take 1 or 2 streams. But it would be kind of fun to have. I think the plan is to try and create basically this little seal here that just happens to be shellcode that pops a shell in a Linux machine. I think it's a plan for the next stream. So Galvanized asked a question, is this what I do full-time? No, my day job is to do development for the most part. So I do not sit here and bash on Python all day, every day. For the most part, I'm just a developer, nothing super interesting. This is most of this is as a hobby, picking it up, doing a lot of CTF stuff. Mostly from CTFs, not from bug bounties. So the bug bounties I think are a good way to get into it now, especially after you've learned the basics. But at least when I was learning things, they weren't really mature enough to make much sense. Like, I think when I was playing CTFs originally, 7 years ago or something, the bug bounties around then were basically non-existent. I could go find Chrome bugs and get like $100, and that was about it. I'm exaggerating a little bit. I think it was 1,000, but there really wasn't much out there. Whereas today, you can go out and you can find all sorts of bug bounties across all sorts of things. Would definitely recommend looking into that if you are looking to go from simple stuff to try and learn real world applications for a lot of this. Would recommend. Yeah. Like I said, I think it's about everything for this stream. If you guys have any questions, comments, definitely follow me on Twitter, send me a message. Let me know if you've got any thoughts about this or thoughts about future things. I have done a little bit of discussion down on I can't get my mouse to go over there, can I? The Mastodon instance, the pwning.social, about my thoughts for the following stream after the shellcoding one. I'm still playing with the idea there, so I don't want to put too much out there, but I've discussed it a little bit. We'll see where it goes, though. So any case, I will see you all in, I guess it's about 9 days, not this Wednesday, but the following Wednesday, when we're going to take a look at some shell cutting stuff. So, thanks again for everybody for tuning in, and I will see everybody around. Bye!